I'm delighted to introduce, where is he? Ben van Calster, who I noticed was wearing a tie yesterday, which was quite shocking. Now, Ben is a professor in KU Leuven. He is not a clinician, so don't ask him any questions about ultrasound. He is a biostatistician, and he has really been the driving force behind all the statistical approaches to IOTA. And he's going to talk about the ADNEX model, which I think many of you will have read about, which instead of dividing or trying to separate tumours into benign or malignant, can subclassify masses into stage 1, borderline, metastatic, and so on. So it's a sort of new approach to how to examine ovarian tumours. So quite complex statistics, but Ben always makes it very easy. Over to you, Ben.
Okay. Good morning, everyone, or, well, good morning, yes. How does this work? Oh, this is a pointer, yes. I have to wake up. So indeed, I'm the IOTA statistician, and I will try not to ruin your day by listening to me. But actually, during the coffee break, I already ruined one person's day, and he experienced the dangers of coming close to a statistician because I spilled his entire cup of coffee on his shirt and on his shoes. So be careful when you see me. Anyway.
That's quite significant then, really.
It's good that I didn't hear that. I'll start with a short analogy with the weather. So if you're interested in the weather for tomorrow, then the first thing you might ask is whether it will be good or bad. And if the weather is bad, you might decide to stay inside and open a nice bottle of wine. But actually, in many situations, people need more than simply knowing whether the weather will be good or bad. Such as pilots, they have to know what kind of weather it will be. And this is basically what the ADNEX model is doing. So existing models make a distinction between benign and malignant tumors. But the ADNEX model goes into more detail by predicting the probability that a tumor is benign, borderline, stage 1 cancer, advanced stage cancer, or secondary metastatic cancer. Right, and the ADNEX model makes a prediction based on 9 predictors. 3 are clinical predictors, age, serum CO125, and type of center. And then 6 are ultrasound predictors. So maximum diameter of the lesion, the proportion of solid tissue, which is computed as the maximum diameter of the solid part divided by the maximum diameter of the lesion, whether there are more than 10 cyst locals or not, the number of papillary projections, which is either 0, 1, 2, 3, or more than 3, whether acoustic shadows is present, yes or no, and whether ascites is present, yes or no. Now, we got some confusing comments about using type of center as a predictor in a model. Now, some short information about how predictors were selected. And we did this a priori. So we did not use statistics, which might be strange for me. But actually, statisticians agree that using a priori knowledge by experts, such as people in the IOTA steering committee, is in fact more important than simply relying on statistics to select variables. So this is how we did it. A priori, we selected 10 variables, and then later on, 1 variable was removed statistically. And we focused on predictors that have potential predictive value, of course, but potential predictive value for distinguishing between type of malignancy. And we focused on predictor variables that we think are more objective than other variables. And so for that reason, we deliberately omitted some variables such as variables related to vascularization, which may be more subjective. One of the predictors that we selected was a type of center. And this was divided into oncology centers or other centers. And the definition of an oncology center was a tertiary referral center with a specific gynecology oncology unit. But then the question is, well, if the same patient comes to my center, and it's a regional hospital, and then later that day, that patient goes to the center across the street, which is an oncology center, then the estimated probabilities are by definition different, even though the patient is the same person with the same tumor. So that might be confusing. Of course, people typically end up in an oncology center or another center for a reason. It's not purely random. You have some referral patterns that come into play there. So that's one reason. And ADNEX contains 8 patient-specific predictors, but even then, type of center is predictive of malignancy. Fortunately, it is the weakest of all 9 predictors. So it is predictive, but fortunately, the 8 patient-specific predictors capture most of the predictive information that we have. Type of center then might be a surrogate for clinical signs of malignancy that are not present in ADNEX, but that help or that made patients end up in an oncology center more often. So that is some interesting issue to look into in the future to see whether we can find such clinical signs that can further explain the importance of type of center. But apart from that, including type of center improves the reliability of risk estimates because the risk of malignancy, even after controlling for the 8 patient-specific predictors, is still higher in oncology centers. Okay, this is a plot where I try to show the ADNEX model on one slide without statistics, so only colors. And I don't know if I will succeed in explaining what it means, but you have the 9 predictors here the left-hand side. And you have 9 columns, one for each type of malignancy versus benign tumors. And so for every predictor, you have a color bar that indicates how much the risk of that malignant subtype increases as the value of that predictor increases. So for example, CA125 is important for discriminating benign tumors from advanced stage cancer because the color of the color bar moves from light yellow to red. On the other hand, age here is not really important for discriminating benign tumors from borderline tumors because the color stays light yellow across the whole range of the color bar. So in that sense, you can see which predictors are most important for which type of malignancy. You can see that all predictors are positively related to malignancy except shadows, because there the color decreases from reddish to yellowish rather than the other way around. And so you can see that for borderline tumors, maximal diameter of the lesion, number of papillations, shadows, proportion of solid tissue are most important. For stage 1 cancer, it's mainly a maximal diameter of the lesion, but then also a proportion of solid tissue, maybe also shadows. For advanced stage cancer, it's CA125, proportion of solid tissue, age, maximal diameter of the lesion. And for secondary metastatic cancer, it's maximal diameter of the lesion and proportion of solid tissue and shadows. So you see that the strongest variables are the same for in most cases. But I hope that this figure gives you an impression of how ADNEX arrives at its risk estimates. Then a word about CA125, because I understand that CA125 is not measured routinely in certain centers, but ADNEX can also be used without CA125. And the consequence is that, in fact, the classical discrimination between benign and malignancy is not very strongly affected, so that's good. But discrimination between advanced stage cancer and other malignant subgroups is more difficult or is worse if you don't have the CA125 value in the model. So we've put the ADNEX model in an app available on iTunes and Google Play. And so you can simply enter all the predictor values on one screen, and then you get the results on another screen, where you can see 2 color bars. The first color bar gives you the baseline risks of a benign tumor in green, borderline in yellow, stage 1 cancer in orange, advanced stage cancer in red, and secondary metastatic cancer in brown. And at the right-hand side, you see the risks for the specific patient for which you have entered the values. And then you can also get these very fancy radar charts that basically shows the same thing, but in another way. Now, how should we use the ADNEX model? Because it's more complicated. You get 5 probability estimates rather than just a risk of malignancy. For this topic, I liked a recent paper in British Medical Journal about evidence-based medicine. And one of the quotes in that paper was that real evidence-based medicine demands individualized evidence, is characterized by expert judgment rather than mechanical rule following. Now, I assume that most people in clinical practice will not simply rely on a model and ignore their own opinion. I assume this is the case. But this quote for ADNEX, I think, means that, in my opinion, you should not use a model like ADNEX to classify a patient into one of 5 groups and then select management, assuming that this classification is correct. You should rather check for which types of malignancy the risk is high, and then see what you can do for each type of malignancy separately. And this is described in more detail in the paper in the Facts, Use and Vision journal that you got this morning. A second thing is that I think you should not use fixed cutoffs, not for this model or not for any model, because cutoffs depend strongly on national healthcare practices, for example. They depend on the specific aim, the specific type of center where you are in. So I think that cutoffs should be, to some sense, flexible. In that sense, I think it's important to say that a cutoff is not an inherent part of a model. I have the impression that some people think it is, that LR2 means that you have to use a 10% risk cutoff. It's a suggestion that we made, but you don't have to do it. So I think that's good to know. So for example, if your aim is to select patients for expectant management, you may choose a relatively low cutoff, even as low as 1%, for example. On the other hand, if your aim is to select suspicious tumors for referral to a skilled gynecological oncologist, you may go for a higher cutoff, such as 10% or 30%. And for ADNEX, you may come up with a 2-step approach, where, for example, first you look at the risk of malignancy, which is in fact the sum of the risks of every malignant subtype, or 1 minus the risk of a benign tumor, if you are interested in mathematics. And then first you can see whether the risk of malignancy is high enough, and if it's below a cutoff that you're using, you can consider the mass to be benign, and then you can choose what you think you have to do best in that situation. And if the risk of malignancy is above the cutoff, you can consider the mass to be malignant, and you can make a decision based on that. And so for this first step, CA1 to 5 is preferable, but not really, well, it's not unavoidable, let's say. But for example, if the risk of malignancy in the first step is high enough, then you may still measure CA1 to 5 for the second step, which is then where you look at the risks of different types of malignancy, and there CA1 to 5 matters more. And then you can see for every of the 4 types of malignant tumor whether the absolute or the relative risk is high enough. And if it is, you can take some specific action for that. And with relative risk, I mean the risk relative to the baseline risk that you saw in the app that I showed before. And the relative risk is simply the patient risk divided by the baseline risk. So I show here one example. It's a patient that's 32 years old. She's scanned at an oncology center with a CA1 to 5 of 9, maximal diameter of the lesion of 13 centimeters approximately, a maximal diameter of the solid component of 9 centimeters, no papillations, 1 local, no acoustic shadows, with ascites, and also with irregular cyst walls and with very strong flow. These last 2 variables are not in ADNEX, but they are in some other models. That's why I showed them here as well. And I give here the result of some models. So RMI gives a rather low value because it's a premenopausal patient with a very low CA1 to 5. LR2 gives a risk of 86% that it is malignant. Simple rules classify it as malignant. And then ADNEX gives 32% that it is benign. It gives a risk of 21% that it is borderline. And this risk is 3.4 times higher than the baseline risk, which you can see in the plot. It gives a 26% risk of being stage 1 cancer, a 7% risk of being advanced stage cancer, and a 13% risk of being metastatic cancer. And this patient actually had a stage 1A cancer. And so the relative risk for stage 1 cancer is the highest, and among the malignant subtypes, the risk of stage 1 cancer is also the highest. But you can see that for different malignant subtypes, the risk can increase relative to the baseline risk. So in that sense, I would say do not classify a patient into one group, but simply look at the whole picture. This is a second example. This patient is 52 years old, scanned at an oncology center. CA125 is 103. Maximal diameter of the lesion, 11 centimeters. And this is the same as the maximal diameter of the solid component. So no papillations or locules because it's fully solid. No acoustic shadows, no ascites, irregular cyst walls, and moderate flow. Here RMI is also high. LR2 gives 71% risk of malignancy. Simple rules say it's malignant. And then you can look at the ADNEX risks. And here you can see that the risk of a borderline tumor is decreased relative to baseline, but the risk of the other tumor types is increased, and the largest increase is found for metastatic cancer. So the absolute risk of a metastatic cancer is 16%, which may not seem that high, but it increases 4 times relative to the baseline risk. And this is simply because there are not that many metastatic, secondary metastatic cancers. So you start from 4% baseline risk. So it's very hard to get a very high risk for an individual patient for this type of tumor if you start from 4%. So therefore the relative risk can be informative. And so for this patient you may check whether there is a primary tumor in another origin, for example. Now if we validate the ADNEX model on the IOTA-3 data, we get the following RC curves. So for ADNEX we have 0.94 AUC with CA125 and 0.93 AUC without CA125. And this is an AUC curve for benign versus malignancy in general. So you can see that if you omit CA125, AUC decreases a little bit, but not that strongly. And then you have these AUCs for every comparison of specific tumor types. So a lot of bars on this plot, but I think most AUCs are pretty high, are above 0.80, above 0.90. But for some comparisons, it's a bit more difficult to discriminate tumors. For example, to discriminate stage 1 ovarian cancer from secondary metastatic cancer, the AUC is 0.71. And to discriminate stage 1 cancer from borderline tumors, the AUC is 0.75. So these discriminations are the hardest for ADNEX. But in general, the AUCs here look very, very reassuring or quite high. And then I also show some sensitivity and specificity values for several cutoffs, because I said that, in my opinion, a cutoff should not be fixed. So I give here 5 cutoffs, and you can see, for example, for the 10% cutoff that we always use for LR2, you get a 97% sensitivity and a 71% specificity. So in general, this is quite good. And then something that was performed very recent is an external validation of ADNEX in the hands of examiners with varied training and experience. So this is comparable to the IOTA-4 study where we validated LR2 and simple rules in this kind of setting. And here we have some data from 3 oncology centers from London, Southampton, and Catania in Italy. And so basically this study is a pragmatic assessment of ADNEX in a real-world clinical practice where several people work together. And generally the operators are of F-simple level 2. I have to say that I'm not I don't know exactly what the definition of fsimple level 2 is, so I'm sorry for that. And data were collected on an Excel sheet with a built-in ATNEX calculator. So this is very recent stuff, and we did our best to get results ready by today. And I have to thank Bavo for the help with the statistical analysis for this data. So in this study, we have 751 patients that are scheduled for surgery. 140 are excluded for several reasons that are listed on the slide. So we end up with 611 patients that are included. And we have 70% benign tumors, 7% borderline tumors, 8% stage 1 cancers, 11% advanced stage cancers, and 4% secondary metastatic cancers. As you can see, as a statistician, of course, I'm not satisfied with sample sizes like this. So you have to be careful with assessing discrimination between tumor types with fairly limited sample sizes, but it is still a good exercise to do in this kind of setting. And so here are the ROC curves for the general discrimination between benign and malignant tumors, for which sample size is adequate. And if you remember the ROC curves that I showed for the IOTA-3 validation, then you might notice that the curves here are very similar. The AUCs are a little bit lower, but it's really almost on the same level, so that's very nice. Here again, a similar plot for the discrimination between different types of tumors, and you probably do not remember the plot that I showed for IOTA-3, but if you would go back, you could see that the plot is fairly similar. And actually here, all AUCs are about 0.80 or much higher. So that's also reassuring, but there is a lot of uncertainty because of limited sample sizes for specific tumor types. So you have to keep that in mind always. And then I show also the same results for sensitivity and specificity for the same cutoffs. And also here, suppose you remember the table that I showed for IOTA-3, you might notice that the results are again very, very similar. Okay, so I've explained the ATNEX model. I've given some of our views on how the model can be used. I've showed some examples, and I showed some validation data of the performance of the ATNEX model. And now my last slide is this nice colorful slide, but it requires again some explanation. So here I've split up the tumors in the IOTA data set by specific histology. So we have about 11 benign histologies and then 7 malignant histologies. And for all of these histologies, I computed the average risks for every tumor type given by ATNEX. So for example, the green bar gives you here the average risk of being benign that ATNEX gives to the endometriomas in the IOTA database. And you can see that the average risk of being benign is more than 90%. And the average risk of being any of the malignant tumor types is somewhere between 1% and 3% approximately. And so in this sense, you can get an idea of where, for which types of histologies that ATNEX works very well and where it has more difficulties. So I think it's an interesting graph. You can see that for several benign histologies, the average risk of being benign is around 90% or more, but that ATNEX has some difficulties for specific histologies such as abscesses. The average risk is still high, but it's I think a little bit lower than 70%. So the average risk of being malignant that ATNEX gives to abscesses is about 30%. So that's quite high. For fibromas, we have a similar picture here. So these are types of tumors that are more difficult, but if I remember correctly, fibromas often have lots of solid components. I hope I'm not saying anything ridiculous here, but in that case, that explains why ATNEX gives higher risks for malignant subtypes. Rare benign tumors here are also a little bit more difficult for ATNEX. Then if you look at borderline tumors, for example, and we've split them up into stage 1 borderlines and advanced stage borderlines, you see that the average risk of being borderline is increased relative to the baseline risks, which is of course good, otherwise the model would not work very well. And you see that for advanced stage borderlines, that the average risk of being benign is smaller than for stage 1 borderlines, and the average risk of being advanced stage cancer is higher compared to stage 1 borderlines. Then if you look at ovarian cancers split up by stage, you can nicely see that the average risk of being advanced stage cancer is smallest for early stage cancers, fortunately, and then is higher for the advanced stage cancer, and it increases by stage. That's good to see. And the average risk of being stage 1 cancer is highest for stage 1 tumors, and it decreases with increasing stage of ovarian cancer. And then finally, for secondary metastatic cancers, you can see that the average risk of being secondary metastatic cancer is highest for this group. Such that, but again, you can see that the average risk here is about, let's say, 11%. This may seem very low. You would hope to see that secondary metastatic tumors would get a risk of 80% that they are secondary metastatic. But as I said, this is very difficult given that the baseline risk is only 4%. So you really need a hugely predictive model to get predicted risks of more than 50%, let's say. So in that sense, 11% is like a 2 or almost 3 times increase relative to the baseline risk. But I think this graph gives some insight into how ADNEX works for different histologies. And well, I hope I was able to explain this a little bit clearly for you. And with that last slide, I conclude my talk.
Ben, thank you very much. It really is. It's a fantastic piece of work, ADNEX, I think. Questions from the floor? Thanks very much, Wouter. They're terrified I'm going to turn the AV off now, you see. Well, we've got people. Usha, because the microphone's nearest to you, and then we've got Lil Valentin. So, Usha Menon.
Ben, thank you for a very clear talk. I just wanted to ask you about specificity, because I was a bit concerned that if the specificity is 68%, that would mean that a huge number of benign cases would be going to gynae-onc centers. And I guess that is important in a health service all over the world, which is stretched for money, because operating in a gynae-onc center costs are much different from operating in and there would be impact on cancer care because it would impact on waiting lists and stuff. So the specificity in the hands of non-experts seems to have really dropped. Do you feel that to have come down, the specificity of ADNEX?
It has gone down?
In this?
No, it's actually fairly similar to what we found in IOTA 3.
Is that because you haven't put confidence intervals?
That's a very important comment, and I would like to go into this because, like Ben says, cutoffs are not really
10%
fixed.
cutoff,
Yes.
Because what would be really helpful if you could say number of operations per cancer detected as a third column, that would help very much. You know, then you can, on the 10% cutoff, if it's 68%.
Yes, but it's really depending on your national guidelines and on your national situation. In the UK, in the Netherlands, some countries, the access to gynae-oncologists is very limited. So then you need to make sure that you use a cutoff which is closer to, for example, 30%, and then you will refer most patients, 86% with cancer, to the oncologist, and then you have few false positive results. So the burden to the gynae-oncology units is not becoming too much. On the other hand, in other countries where there's a lot of gynae-oncologists or more private practice or more possibilities to do so, then you can say, well, we really try to refer all patients with cancer to a gynae oncologist in order to make sure that patient has the best prognosis. So this is really for each country to decide which cutoff will we propose for our healthcare system. And if you go for conservative management, then you don't want to miss cancers. Then you use the cutoff of, for example, 1% or 2%, and then you can say everything below 5% or everything below 2% is for conservative management. And if it's above 30%, we refer to gynae oncologist, and between 2% and 30%, general gynecologist will operate. That's something that could be possible, but we cannot decide this. We can only offer the figures, and then every country has to decide what they will do.
Because, I mean, if you look at RMI, I mean, the sensitivity for RMI at best is 71%. Yes, but well, of course, because that's how it works. But this is the old nonsense about CO125 going back years, is that you don't want a test that misses cancer. I would argue that if you look at the UK data at the moment, only 70% of people get operated on by a specialist. And one of the reasons for that is because people use RMI, which has such a poor sensitivity. I mean, I would take a straw poll of women in the audience, and I would say that they would much rather make sure their cancer was detected and operated on by an expert and end up in a cancer centre than have a slightly lower chance of, a slightly higher chance of their benign cyst ending up in a cancer centre, which possibly would have secondary imaging and in any event wouldn't end up harmed. So I think you've got the wrong approach, actually. I think you're looking at it the wrong way round. I think sensitivity is a critical issue. I think most women want their cancer detected. You don't need a test for cancer to tell you haven't. You know, it's the wrong way of looking at diagnostic tests, in my view. Question there. Sorry, Lil. Excuse me. Can I take Lil Valentin next because she was second? Sorry. I'll come back to you. Thank you.
Actually, I have a question on the study design, and it isn't to say that it is very important, but I would like to know, when the examiners collected data for this study, did they know that they were actually prospectively validating the ADNEX model, or did they just enter the variables?
This is for the external validation study that we presented in.
I think about 70% of them, about a third of them didn't. They knew they were collecting the variables for models. One of the ADNEX variables, which is multilocular number of locules, they didn't collect knowing it was in ADNEX. In our unit, they were aware that this data would be used for ADNEX. So did they kind of apply ADNEX? No. Did they collect variables with a view to knowing that they would be validating ADNEX? Yes, they did. But a third, no, they didn't. And in some of those cases, we had to go back and just look at the locularity in some of those cases. And those were cases from Southampton. But I would say in the majority of cases, they were aware that that's what they were validating. But they didn't fill in an ADNEX score and come up with a kind of result, which I kind of think is what you're getting at.
Yeah, I want to know how many variables they collected. Did they collect variables for all the variables for LR1, for example? Did they collect all the variables?
Yes.
And some of them didn't know really for what purpose?
Some of them? I didn't hear you, sorry.
No, I know. The acoustics
the microphone's
is
a bit odd.
difficult.
I couldn't hear you.
Some of them did not know that they were actually collecting variables for the ADNEX, for example.
Yes, some of them. They were mainly in Southampton.
Yeah.
Yes, exactly. Yes.
Okay, thank you.
Ben, it's me. Can you comment on the fact that color score that mattered in simple use and logistic regression and even pattern recognition didn't reach statistical significance in the ADNEX model? This was strange for me.
Well, so the question is why the color score is used in, for example, LR1 in simple rules and in other methods, but it's not used in the ADNEX model. Well, that's the answer is related to our approach for variable selection. We did not statistically select the variables. So it's not based on significance. If you would do some stepwise selection, which is very well known, but is actually not a good method to select variables, unless you have lots of data, then it would be significant, I'm quite sure. So it is very predictive, and it's an important rule or feature in the simple rules. But here we deliberately did not include it in ADNEX because it is a more subjective variable, and we hoped that most of the predictive value of color score would be captured by other variables that we included and that we thought were more objective or more easy to measure by different people. So, but it's a deliberate decision to leave it out, but statistically, I assume it would be selected. Yeah.
Gentleman there who's been waiting a long time.
The question's been answered.
Sorry, it's been answered. Ah,
The question
okay,
has been
fine.
answered.
Sorry about that. Excuse me. Question there. Gentleman raising his hand to take the mic there, please.
Hi, I'm Beto from Italy. Just a question about the follow-up of the patient. It's more important to focus on the probability risk or the relative risk, because on your last slide you show us how you split all the different kind of masses, but for example, stage 2 ovarian cancer, it's really look like the secondary metastatic cancer. And in the second case report you show us, well, it was an old woman with a secondary cancer, but this hypothesis rise from the relative risk, while the probability risk was supposed to be a primary ovarian advanced cancer. So which is most important?
Well, which is most important? Let me say first that the absolute risks that you get here, these, if your model is okay, these should be correct, more or less. So that means 16% risk of metastatic, secondary metastatic cancer would mean that if you take hundreds of patients like this one, that on average 16 per 100 would actually be a secondary metastatic cancer. So in that sense, this is the basic information, and that should be correct. However, it is sometimes not easily acknowledged that you start from different levels in the beginning. So the baseline risk of a benign tumor is about, it's here, 68%, is it? Or so this is much higher than the baseline risk of a metastatic tumor. So it is quite easy to go, well, quite easy, it depends on the application, but it's more easy to go from a baseline risk of 68% to a patient-specific risk of 90%, let's say. But for secondary metastatic cancer, this is almost impossible, I would say. You would need an almost perfect test to get there. And if you remember the AUCs, they are actually much higher than I thought they would be. So the model discriminates very well between each tumor type. But still, you should not expect that the risk for secondary metastatic cancer will go up to 60, 70, 80% for these kind of tumors. And in that sense, the relative risks become important because these put things in perspective. You can still see that the risk of secondary metastatic cancer is clearly increased compared to baseline. And so in that sense, I would say that, well, they both have their strengths. Absolute risks, they are the true risks, so that's what they're supposed to be. It's an estimate, so I don't know the truth. So it's an estimate, it's supposed to be correct. But these take into account the different baseline risks. And it can help you to see which risks are increased and which are decreased for that patient.
Can I comment on this?
No.
I agree that the risk is most important, the relative risk is also important, and we tried to put this into the paper in your Congress book, Infectious Views and Vision. This is more about practical use of the ADNEX app. And then we try to say, well, as soon as you have a relative risk for metastatic cancer, then it's important to exclude the presence of a Kuchenberg tumor. So then in the workup of your patient, you might need to do mammography, colonoscopy to exclude a primary tumor, like a primary breast cancer or so. But again, we came to no conclusion because it was said this is again something for national guidelines, because that depends on the availability of mammography and other types of pre-operative examinations. And some are prone to take more risk to miss this primary cancer, and others say, no, we want to detect every metastatic cancer prior to doing debulking surgery. Because we start doing debulking surgery and then we find out that it's a metastatic breast cancer. It doesn't make sense. So therefore, at a certain cutoff level that you can define, you do extra tests like mammography, colonoscopy, and so to make sure that it's not a metastatic tumor. So AdNext is helping you, but it's not making the real diagnosis instead of you. But from a certain cutoff, you can say, now I will do extra tests to make sure it's not invasive cancer, but a metastatic cancer.
Okay, thanks, Dirk. One last question.
I wondered what your thoughts were about the risk for borderline 1 and 2 and 3 and 4. Simple rules classify number of papillary projections 4 or more to go into the malignant category. In the AdNext model, we have to record the number of populations. Sometimes when there are multiple populations, it's difficult to count the number of populations. How accurate does one have to be, and how much of a weightage does that score in the AdNext model give you? Thank you.
Well, as a statistician, I can say something statistical about this.
But,
if the more, what?
you only need to count to 4.
Yes. So
it's 1, 2, 3 or more. So you don't need to count to 7. So it's very limited.
Yeah, so it stops at 3 or more in the IOTA data collection. But of course, the more inaccurate a variable is, the lower the AUC will be, because this uncertainty is counted in the statistics, and you will see worse discrimination. So if you can be more accurate, I don't know how easy it is to count populations. Probably it's not always that easy.
Much harder than statistics, actually. Really.
Is it? Yeah. What can I say? Yeah.
Okay, well, I think, Ben, before we finish the session, and everyone always gets up and runs away, I just wanted to say there is a lunchtime-sponsored symposium on risks and recommendations for cleaning and disinfection, which is a new approach, apparently. It's quite an important issue in ultrasound, so have a look at your program, and that is a sponsored session over lunch. I just want to thank Ben for speaking. Thank you very much. Now, you have a nice European-style lunch break. We don't know that in the UK, so it's an hour and a half. And we expect you back here at 2 o'clock, I think. So look forward to seeing you then.